Number 1, state the zeros of the function given by f of x equals x plus 3 times x plus 1 times x minus 2. Graph y equals f of x below. So state the zeros of this function. Well, this function's already in factored form, so I know the zeros are x equals negative 3, x equals negative 1, and x equals 2. Because when I plug those values in for x, that factor equals 0. 0 times anything is 0, so the function outputs a 0. Graphically, where do we see those zeros? Those zeros are the x values of where the graph crosses the x-axis. So I have x at negative 3, negative 1, and 2. That's where those are points on this function because those are the zeros. It actually wants me to graph it. It doesn't say sketch it, it says graph it, which means I need to go to my calculator and type this function in. So on your TI-83 or 84, to graph something, we go to y equals and we type in x plus 3 times x plus 1 times x minus 2. We hit graph. Ooh, there's that pretty cubic polynomial there. And that's what my graph should look like, but it'd be really helpful if I had a table of values. It'd be really helpful if I had a table of values to use. This looks like a pretty good table to use here. I copy that onto my smartboard file so I don't need to flip back and forth. So this table of values kind of captures how this graph behaves. So now that I have a table, all I have to do is plot these points. I have negative 4, 18, which means I can't plot negative 18 on here. But it means the function's coming up like that. Negative 2, 4. Negative 1, 0. 0, negative 6. 1, 2, 3, 4, 5. Negative 6. Negative 8. And then 2, 0. And then 3, 24 means it goes up forever. So the function is doing something like this. This is a pretty good graph of y equals f of x. We have that end behavior displayed of what's happening at each end, and I have those zeros clearly highlighted. It's clearly not a perfect graph because I can't plot every single point, but it gets that overall shape of the function. Number 2, algebraically determine the zeros of the function f here. Sketch this function on a set of axes below. So this time I'm just sketching it. I'm not actually graphing it in my calculator, plotting points. I'm sketching to get the overall shape and key features. So algebraically determine the zeros means I'm going to set this equal to 0. And factor. Well, there's 4 terms, so I'm grouping. Take out an x squared from those first 2. Looks like I need to take out a minus 1 here. And like 99% of the time, we get the difference of perfect squares here. X plus 1, x minus 1. So my zeros are x equals 2, x equals negative 1, x equals 1. So now that I have my zeros, I know this function intersects the x-axis when the x value is 2, negative 1, and 1. So at those 3 points, I know the graph of the function has to pass through. Now, if I look at a sketch of this, if I type that into y equals x cubed minus 2x squared minus x plus 2, and I look at a graph of it, I get this overall shape here. Notice that the y-intercept is 2, which makes sense because that's the constant term of this function. If I plug in a 0 for every x, they become 0, and I have a y-intercept of 2. So the function, the graph of the function, let me make that better, looks something as such. Just a sketch. I didn't actually plot real points here. I just sketched it out. Number 3, let f of x equal x to the 4th times x plus 1 to the 7th times x minus 1 squared. State the zeros of f and their multiplicity. Well, it's already in factored form. So the easy ones are x equals negative 1. That comes from that factor. X equals positive 1. That comes from that factor. And this is just x equals 0. When you have a plain old x like that, what 0 does it give you? It gives you back x equals 0. Their multiplicities is how many times does that happen. This has a multiplicity of 4. There's 4 of those factors. This has a multiplicity of 7. And x equals 1 has a multiplicity of 2. Determine if f passes through the x-axis or is tangent to the x-axis. Well, you're tangent to the x-axis if you have an even multiplicity, and you pass through if you have an odd multiplicity. So the function's going to hit x equals 0 and be tangent to it and turn around. It's not going to cross through. It's going to touch x equals 0 and then turn back around. X equals 7, it's going to pass through. It's going to cross through the x-axis because it has an odd multiplicity. And x equals 2 is an even, x equals 1, sorry, has a multiplicity of 2 is even, so 2 is even, so that's going to be tangent. It's going to touch the x-axis and then turn around. So it's just understanding that multiplicities affect the graph by determining whether the function passes through at that 0 or if it touches it and turns around. Number 4, create the equation of a cubic polynomial. Remember, cubic means x to the third polynomial, so I want a degree 3 polynomial here that has x-intercepts of 4, -3, and 2, and that has a y-intercept of -18. So if I have x-intercepts of 4, -3, and 2, those are my zeros. What factors gave me those zeros? Well, I better have had a factor of x minus 4, a factor of x plus 3, and a factor of x minus 2. It's an equation, so I need y equals. However, there's always a leading coefficient out front that we don't know what it is, so I'm going to put an a there. This a can be any number. I want the y-intercept to be -18. So when I plug in 0, I want to get out -18. When I plug in 0 for x, y has to give me -18. So I'm going to say -18 equals a times 0 minus 4 is -4. 0, I'm plugging in 0 for x. 3, -2. When I multiply those all together there, I get -12, +24. Divide by 24. And get -18 out of 24 is a. So that's my leading coefficient. However, -18 out of 24 is better known as -3/4 if you simplify it. So what's my actual equation? Y equals -3/4 x plus 4, sorry, x minus 4. All I'm doing is I'm plugging that -3/4 in for a there. X plus 3 and x minus 2. That's the equation of this cubic polynomial. It doesn't look like x cubed, but there are 3 factors, which means it is an x to the third. Number 5, sketch a graph of p of x equals x plus a, x minus b, x minus c, if b is bigger than c on the set of axes below. So let me draw a sketch of a set of axes. Well, it's in factored form, so my zeros are x equals -a, x equals b, and x equals c. So we're going to assume that they're all positive. We're going to assume a, b, and c are positive, which means that there's -a. B is bigger than c, so who should come next? B is positive and c is positive, so that's over here. B is bigger, so B is going to be there, and that's c. If you picked your favorite numbers and plugged those in, you're going to get a graph with that type of shape. So sketch a graph of p of x. The key thing that I want you to recognize here, if those are my factors, these are my zeros. We have to assume here that a, b, and c are positive. I left that off. Hopefully you feel comfortable with graphing polynomials. The key thing is noticing that relationship between the factors and the zeros. And the zeros are the x values of the points where the function hits the x-axis.